Welcome back to part 2 of the lecture 15, High Performance Computing, Advanced Scientific Computing course. In the first part, we talk about the history and background of the quantum mechanics and how the idea from the quantum computing started. In the second part, we will have some review on the quantum computing, qubits, superposition and entanglement for the state for the qubits, and then we will have a very brief look on the IBM quantum computing with a simple example. In the beginning, let's talk about the quantum computing, why we need to use the quantum computing and what it makes it important. Let's have two examples from the classical computer limits. There are two main area which quantum computing it's make do the computing possible. One of them, the optimization. The optimization usually the process of finding the best solution to a problem from a set of possible options, given its desired outcome and constant. As you know, in the optimization, when we have a problem, we have different option, different possibility. We are looking for the best one. Sometimes the superposition or the state or possibility of the state, there are too many. So to find between these different states, among all of these states, the best option, it's need many computing. Quantum computing has this capability to do this solution and find the optimization. About the number of the possibility, let's have an example. Assume we have a problem with 10 factorial configuration. That means we need to go through 3 million states. This is really a very large number of the computing. And of course, when we're increasing the configuration, it's 10, so it's changed to 20. It's increasing logarithmic. So this is one of the area which quantum computing has a capability, because as we said, the qubit has a superposition, so we can have a superposition for the different scales. And its possibility with the change of the phase, it will be able to find the optimization faster than the classical computers. The another one, the simulation. In some areas, the simulation need extensive computing. One of the example is in the chemistry regarding the molecules. We need to calculate for every single electron and forces. You can imagine how many electrons in a molecule, and we need to calculate the forces between them. And the number of the molecules on the specific area when it's increasing, so we can imagine how many electrons and how many forces will be. So the huge computing and increasing logarithmic. There are many examples in the chemistry. They studying about the molecules, and the simulation is really extensive. Quantum computing, based on its architecture and the concept, it's able to solve this type of problems. But how it's behave and how it's working, as we said, we have the qubits in the quantum computing. Regarding the qubits, how they are working, we know from the uh, classical computing, we have two possible value of a bit. It's 0 and 1. And in here, in this figure, we can see in the left-hand side, figure is presenting these values. We have two state. It could be 0 or it could be 1. But for the qubits, as we said, there is a possibility for the superposition. And we can have a superposition of two different states. Here, these only presenting zero state, this one presenting state one, but this one, as you can see, it has a different superposition for 0 and 1 state. Usually, for the bit, we can say we can initialize a bit in either state 0 or state 1. These make the mathematics of binary logic simple enough. And we see in this figure how it looks like. But when we are talking about the qubits, we can see the different. So we have many different superposition. Here only two representation, but here we can do many different superposition of the states. Regarding the bracket here, in the mathematics, the label from 0 and 1 changed to bracket 0 and bracket 1. The reason is because in quantum computing, usually this bracket notation used. The bracket notation denote values that a qubit might be found to have when readout. When referring to a value that a qubit has been read out to have, we just use the number to represent the resulting digital values. So this is the reason why we are using it in bracket and different with the bit. But how the qubit working and how implementation of a qubit with the device working? To have an example and understanding of these devices, let's first look on the uh, bit in the classical computing. Usually we can have the photon, single photon, to demonstrate the quantum superposition. So let's see how it's working for the digital bit. In this figure, left-hand side, it's example for the bit, as it's shown in this device, a switchable mirror, this one here, which that can be set as either reflective or transparent, allows us to control whether a photon ends up to one or two paths. We have different one. It could be end up here, one, or it could be end up to zero, based on this switchable mirror, as you can see. It could be on the reflective condition, or it could be transparent. So it will lead to a different state of 0 and 1. Devices like these actually exist in digital communication technology. Now let's look how we can determine the photon, single photon for the qubits and quantum computing. This is a very simple implementation of one photonic in the figure in the right-hand side. Here, we are using a half-silvered mirror. Is semi-reflective surface that would, with 50% chance, either deflect light into the past we associate with 1, or allow it to pass straight through to path we associate with 0. There is there are no other options for it, as you can see here. So it's leading to 1 or 0. Uh, it is very easy to misunderstand the nature of the superposition when we talk about the state of the 0 and 1. It is not correct to say that the photon in both the 0 and 1 paths at the same time. It's not possible at the same time. They can be on this same paths. There is only one photon, so if we put detector in each path, only one will go off. When this happens, it will reduce the photon superposition into a digital bit and give a definite 0 or 1 result. So this presentation, in the simple way, determine how the photon could be used to define the state of the qubits. In the qubits state, we have the superposition. We talked about this in the first part and how it's working. Assume for 5 qubits, it's possible to have 32 quantum states, and the paths used with this equation 2 to n, which 2, of course, the state, we have 0 and 1, and the qubits or the path is n, so it will be 2 to n paths or n states. To present graphically the superposition and the state of the qubits, the Bloch sphere is used and is a geothermal representation of the pure state space of two-level quantum mechanical system qubits. You can see here in this slide how it looks like. There is a different phase between different states. And every superposition is presenting one state of qubits. However, we have the entanglement, and we talk about that. The entanglement make it possible to know the another state when you read one state. The state of entangled qubits cannot be described independently of each other, so they have a correlation, and we talk about this in the previous lecture, in the previous part of this lecture. Regarding the building the quantum computing and quantum machines, there are some ongoing research and available machines. This is the example of the IBM quantum machine. As you can see here in these pictures, the qubits make like artificial atoms, and then they during the superconducting, which is lead to around 0 Kelvin of the temperature. It's colder than the space, and then using microwave resonator to address and couple the qubits. So coupling and addressing the qubits with the microwave, it's happening. And here is presentation of these machines, how they are working. And here you can see the contact between the microwave. And this is a huge cylinder, which this system inside of these vessel. You can look on the IBM website, and there are very good information, and there are some videos explaining these machines and how they are working, how they build them, and some ongoing research as well. There is a free service of the IBM Quantum. You can have the account and you can try to see how it's working with the quantum. You have some with free access to some resources from quantum machines, and you can do the simulation, and also its possibility to coding with Python. For example, here we can have a look on the example of this circuit composer, how you can do coin flipping or entangling two coins together. Let's have this example. When you go to your page and creating an account, you will see this dashboard, how it look like. Here the launcher of the composer. When you open this launcher, you can have this uh, environment. Let's do the coin flipping. Here we're opening the new one. And to do that, usually we use the Hadamard gate, which is here. And then we are using the measurement operation. This is like a simulation for the coin flip. We can have a name for this simulation here. Then to run this work to the simulation and see how it's working, here we have access to different machines. As you can see, the system of simulator, they have different name and different capacity. You see how many qubits here. We run it on this machine since we tried it before. It had 32 qubits. Can select it, and there are some settings here. We don't need to do this change, so only run the work. And here we can see how it's going with the work. As you can see here, it's running. When we look here, we should see the state of this job when it's running or it's sent. Of course, it's a live system, and sometimes maybe we can run the work and maybe we can try it again. The another example we can do, let's do the another one. We can do the entanglement for the two coins together, and we try it. Let's do that. Again, we are using this block. So to do the entanglement between them, this is the 0 state, and this is the state 1. We can save the name for this one. We can try to submit the job as well. As you can see, the previous one didn't work, so we can try again. Let's here again choose this one and run this simulation. The previous one. This one we submitted for these entangled coins. As you can see, here is the simulation, and it's presenting the measurement outcome and how the frequency for two different states. And you can do many different simulation for different category and different problem. We can try to look on that job, what's happened for that one. This job, the flip. Let's try this one again. It's still running. And of course, there is a possibility to solve it for this secret. Still, we have error. However, you saw the example for the entangled coin flipping. So you can try this one on your account, and you will see how it looks like. However, there is a possibility to programming with Python as well. So I suggest you, if you are interested in the quantum computing, you can have your account on this online system, and you can have some training. There is some training as well. You can find it on their website. And the quantum computing, of course, is the state of the art in the HPC, and there are many possibilities to doing research and project. And this system also, it's possible to use it to do some for some research, and you can have some measurement on it, and you can report it, of course. And the last part of this lecture is about the quantum computing model. Currently, there are two main models, quantum annular and universal gate-based. They have different capability and the application. Usually, the quantum annular is for optimization. It's optimize the solution to problem by quickly searching over the space and finding the global minimum, which become the solution. So for the quantum, it has this capability, and we said one of the important area we need to use in the quantum kind is the optimization, and quantum annular, it's a model of the quantum computing used in this area. Regarding the universal gate-based quantum, it's control and manipulate the evolution of the quantum state over the time. Complicated quantum systems tend to be incredibly delicate to work. Having enough control means you can solve the most significant class of problems. But universal gate-based, it's limited still. This difference between the quantum annular and universal gate, we can process quantum annular over 1,000 of qubits, but state of the art for gate model only 10 qubits. So this is the important difference between these two different models. So we can say the optimization has a more power so far, and we can have a better computing for the problem with optimization issues. Here there is a video, and you can see how quantum computers work, explaining qubits to quantum superposition, and they presenting information from the real machines. I suggest you watch this video. So here we finished this lecture 15, regarding the quantum computing. Quantum computing is the state of the art in the HPC now, and there are many ongoing research and funding to develop this area, and there are many hope to have the capability from this machine to solve some problem did not solve yet. And this is the last lecture I talked to you. We will continue for lecture 16, and Movies will talk on the last lecture of this course in the epilogue. Here you can see the references, and you can look on them if you're interested. And thank you.